Kia ora. In this video we're just going to have a little bit of a explore of scientific notation and how to deal with significant figures. It's one of these things that's going to kind of apply to most of the course at various points in time, so having it in a separate video means you can come back to this if you're getting a bit confused at another point. Okay, so what do we mean by this? Well, scientific notation essentially is the way that we tend to express numbers, especially if they're really small or really big. So an example would be something like 3.56 times 10 to the power of 10, which is this one here, times 10 squared, sorry, or 3.67 times 10 to the power of negative 4. So you can see, just note down a couple of features here. This number, one number to the left of decimal. So we're going to adjust it so that we have one number in this leading position. It's never going to be 0 point something. When we're using scientific notation formally, then we want to just arrange it so that we have one number and some decimal places after that. Both of these, they have 3 digits. So that is what we call 3 significant figures. Let's make a little note of that, maybe in orange. Okay, so we can see that 3 significant figures basically means that we have 3 digits when we're in our scientific notation. The power of 10 just tells you how big it is. So 10 squared, that just means 10 times 10. So that number there would be 3.56 times 10 squared, which is 3.56 times 10 times 10, which would be 356 expressed in regular notation. This other one, 3.67 times 10 to the negative 4, well, 10 to the negative 4, that means 1 divided by 10 to the 4, which is 1 over 1 with 4 zeros. So negative powers just means 1 divided by positive powers. So that means that 3.67, which also equals 0.0001. Okay, there are 3 zeros, which is 1 less than 4 before the 1. So that means 3.67 times 0.0001, which means that we're going to have 0.000, so 10 to the negative 4, so we've counted 3 zeros, 1 less than 4, 3, 6, 7. Okay, and we can get back to our regular notation this way, but a lot of the time we're going to work in scientific notation because it's kind of just easy to work with. So if we want to write this in scientific notation, 5342.1, that would equal 1 digit to the left of the decimal point, 3421. And to do that, we ended up moving the decimal place 1, 2, 3 steps. So it's going to be times 10 to the power of 3, or times 1,000. And this next one here, that will equal 1 digit to the left of the decimal place, 3.9 times 10 to the power of, well, let's see how many places the decimal point had to move this time. Decimal place moved from 2 steps to the right, so it's going to be 10 to the power of negative 2. Okay, so one of the nice things about this is it lets us see exactly how many significant figures we've got in an unambiguous way. So if I have a number like 1,000, and we want to know how many significant figures this is, really hard to tell because it might just be 1. It might have been rounded to the nearest 1,000, or it might be 1,000 quite exactly. It might be definitely between 999 and 1,001. We can't tell, looking at this, how many significant figures we've got. But if we put it into scientific notation, we could write it, for example, as 1.000 times 10 to the 3, and we can tell for sure now that this is to 4 significant figures. Or maybe it had been rounded to the nearest 100, in which case we would write it as 1.0 times 10 to the 3 to emphasize that we've actually only got 2 significant figures in this case here. So scientific notation is just quite nice to helping us to understand how many significant figures there are. The other thing I'd say about these powers of 10, have we got any spare writing space? No, let's just, I'll just draw at the top. If I've got 2 numbers and I'm going to multiply them together, say 2.3 times 10 to the negative 4 times 5.6 times 10 to the negative, say positive 7. Then the way you do this is you multiply the numbers together, 2.3 times 5.6, and the power of 10 is going to be, you add the exponents, which is the number above the 10. So it's going to be negative 4 plus 7. So that's going to give me 2.3 times 5.6 is 12.88 times 10 to the negative 4 plus 7 is 3. And this is not quite in scientific notation because I've got 2 digits to the left of my decimal point, so that will also be, let's make a bit more space, will also be 1.288, more correctly, times 10 to the power of 4. We've moved the decimal place left by one spot, so we need to increase that power of 10 by 1. Okay, so scientific notation expresses everything in a very standard way, helps us be clear about significant figures, and it also lets us talk about really big and really small numbers without having to write a whole bunch of decimal points like this one here. Okay, now when we're working on any physics problem, like you're working on a word problem of some sort, you'll be given the information for the problem will include some numbers usually. And there are some rules of thumb for how many significant figures to present your answer to, and also what to do with your calculations as you're moving through the problem. So the first one, if you've got multiple steps in your problem and you're trying to work out a final answer, don't round it in between times. Okay, so you might be tempted to do a calculation and then round it and then do the next one with that rounded value. Don't do that because you can introduce extra errors by just accumulating a whole bunch of roundings one after the other. So don't round intermediate results. Pro tip is you can learn how to store intermediate results in your calculator and then calculate with those. And then when you get to your final answer, you'll present that rounded to the number of significant figures in the problem data. In particular, you'd round it to the smallest number of significant figures that was in your problem data, because you can't really be any more accurate than the least accurate thing that you've got in your data. We'll do an example in a second. And then if you maybe have a part B for your question and you want to reuse that value that you rounded and presented, you'd use, once again, the unrounded value to do a subsequent calculation and then round again at the end. Same rule as this, we don't round intermediate calculations. Practically speaking, you can round them. You can maybe round to like a bunch of extra decimal places that more than you're going to present your final answer. So here's an example, just illustrate this. A car accelerates from rest at 4.0 meters per second squared for 4.35 seconds. What is its displacement? So I can see that my data has been presented with 2 and 3 significant figures. This one has 3. So that means we should present our final answer rounded to 2, because that's the smaller of the 2 of them. So I can go ahead and do my calculation using the kinematic equation that's been given to me. From rest, that means my initial velocity is 0. So it's going to be 1/2 times the acceleration. I should put that in. Include the 0 just for completeness. 0 times 4.35 plus 1/2, 0.5 times my acceleration, 4.0 times 4 delta t squared, 4.35 squared. I'll work that out on my calculator, which will be 0.5 times 4.0 times 4.35 squared. My calculator gives me the number 37.845. If I go and do another part of the problem and it wants me to use this delta x that I've calculated, I would use this one, 37.845. If it was a number that didn't terminate like this one did, just take a reasonably large number of decimal places for your subsequent calculation and round at the end. But then when I'm presenting my final answer here, I would present it to two significant figures, because that is the smaller of the smallest number of significant figures I've been given in my data. So that means I'd round this to 38 meters. And you might just indicate that you have presented this to two significant figures. That's the other way we can be explicit about the number of digits. We can literally say how many significant figures there are to avoid any confusion. We could write this in scientific notation, but it would feel a little bit weird. 3.8 times 10 to the 1 meters. We wouldn't tend to do that, just because 38 is a number we've got a handle on. But if the answer had been 40, again, we would have wanted to specify somehow whether that was one significant figure or two. Okay, so hopefully this is going to become kind of clear as we go through the course. Every time we do a problem, we need to think about the two things: don't round intermediate results, and then final answer rounded to the number of significant figures in the problem data. The other thing that we'll mention before we call it quits today is the idea of prefixes. So when we're dealing with very small or very large things, we tend to put a prefix out the front. So for example, let's just write down what some of these are. So pico, you probably won't come across pico very often, but pico is a small one. So the multiplier would be 10 to the negative 12, which means that 1 picometer would be 10 to the negative 12 meters. So if you're converting to standard SI units to do your calculation and your value was 3 picometers, in your actual calculation you did, you'd have 3 times 10 to the negative 12 meters would be the thing that you put into your calculation. Okay, so let's run through some other common ones. Nano, you may have heard of nanotechnology. That is sort of the scale at which you can manipulate atoms and things. So that's 10 to the negative 9 if we're talking about, well, nano anything, but nanometers is that scale of nanotech. Micro, 10 to the negative 6, often looks like the symbol mu. So micrometers are written as micrometers. Okay, let's just add these in here, shall we? So pico is a P, nano is an N, micro is a mu, milli, like millimeters, is a little m, 10 to the negative 3. Centi, we pretty much only use this for centimeters, but it's 10 to the negative 2. Deci, similarly, you might occasionally use this. That's D, 10 to the negative 1. And then we get into the ones that make things bigger. So kilogram, kilometer, 10 to the 3. Mega, 10 to the 6. And some of these you'll know about from computer storage: megabyte, gigabyte, terabyte. Giga is 10 to the power of 9. Tera is 10 to the power of 12, and peta is 10 to the power of 15. There are others, but that's you're going to cover pretty much all bases with these ones here. So 1 terameter, that is the same as 10 to the 12 meters. So you need to make sure you express in a calculation, you want to be in the standard SI units, and if you need to convert a prefix, these are the values that you'll sub in to make it into the standard thing. Okay, and that is enough for now. We'll see you next time. Ka kite anō.